Artificial as well as biological agents can face a large variety of different needs, ranging from self-sustenance to self-preservation, social and empathic skills, external tasks such as navigation, as well as societal expectations such as complying with ethics. Even engineered artifacts rarely ever truly concern just one of these needs, but will face situations where multiple needs create situations of conflict, in which different needs point out different behavioral options. Typical examples of such situations can be found in the conflict between external tasks and internal tasks, such as self-preservation. A robot reaching for an object needs to achieve its task while simultaneously avoiding obstacles at the same time. A navigation system may have to find the shortest path to a destination, but at the same time having to avoid the car driving into a lake, as well as conversational agents that have to engage with an audience while simultaneously having to avoid seriously inappropriate or unethical behavior. Due to the fundamental nature of these kinds of need conflicts, a vast variety of solution elements can be found in literature of existing architectures, starting from classic cognitive architectures such as subsumption and belief, desire, intention, to agents that optimize for one need at a time and switch between them. ICDL has seen advanced models of hormonal dynamics that moderate different needs even in the long run, as well as models specializing on combining positively and negatively valence stimuli, specialize on skills such as avoidance. However, all of these previous approaches are either themselves domain-specific or incomplete in the sense of requiring additional, externally supplied decision rules to cope with a particular environment. Instead of focusing on such specialized solutions, this article looks at the nature of need conflicts, the lens of rational agents. An agent is rational if its behavior is consistent with a globally defined, consistent preference, value, or utility function. Given the range of behavioral options, the agent will always pick that option that maximizes this global preference function. A typical example can be found in reinforcement learning, where instantaneous preference is modeled by a scalar reward and overall preference modeled by the future expected sum of rewards. In the case of multiple conflicting needs, two questions arise. First, how can conflicting needs be modeled with the use of just a single globally consistent preference function? Second, how can such a preference function be used to guide an algorithm effectively to also resolve such conflicts? The idea of reinforcement learning has been applied to the multi-objective or multiple needs scenario in a variety of ways. In the simplest case, rewards corresponding to different objectives are merely added up to constitute an overall reward function. Common practice in reinforcement learning is to give these terms weights that allow a designer to adjust their relative importance. However, this approach is known to be highly susceptible to reward hacking, in which case the agent chooses to optimize one objective fully over another, which is known as a major current issue in AI safety. An extension of this idea involves the dynamic weighting of objectives by time-changing weights, which can lead to highly specialized solutions of specific situations, but does not give a clear model for a globally consistent preference valid over a whole range of situations. Other than linear combinations of different objectives, nonlinear preference functions have been investigated. However, are known to generally require non-stationary solutions that are very difficult to model, control, and learn. Alternative models aim at discovering a whole range of policies, such as an entire Pareto front, on which all policies represent some kind of multi-objective compromise. While these models are very good at describing the nature of a value conflict, they only defer the resolution, the actual decision, to a later subsequent decision mechanism. The contribution of this paper is twofold. First, it proposes an example problem for the study of conflicting needs. This example problem is not meant as a realistic depiction of any particular real-world scenario, but as a highly condensed need conflict that is just small enough of a problem to allow for a comprehensive analysis while being difficult enough to concisely show limitations of previous approaches. Secondly, this paper proposes a new nonlinear preference function called more, which will be shown to both model and resolve conflicting needs, here based on the design premise that needs must be achieved in a balanced manner. The example problem consists of only 3 states and 2 actions. 2 actions corresponding to left and right movement allow the agent to move in between the 3 states. One need, corresponding to food, can only be found in the leftmost state, while a second objective or need can only be found in the rightmost state, so that the agent has to alternate between both states to satisfy both needs. To make the problem challenging, at the same time of gaining on any one of the objectives, it loses on the other, which could correspond to becoming thirsty when consuming food or becoming hungry when consuming drinks. In the middle state corresponding to a corridor, both objectives lose slightly. This presentation will use the interpretation of food and water as an intuitive way to gain an understanding of the problem. However, the algorithm and the results in this paper in no way rely on this being the prime interpretation. We can first investigate how linear reinforcement learning models fare on this problem. The simplest possible case is to only optimize one of the objectives at a time. If the agent only optimizes for food, it will go to the state in which food can be obtained on the left side and stay there, corresponding to a very high overall value in food, but a very low overall value in water. Conversely, we may give the agent the instruction to only optimize the water objective, in which case it moves over to the right, stays there, corresponding to a very high value in water, but a very low attainment of the food objective. A balance may be attempted by adding the individual reward components. However, in this case, because of the larger overall margin on the left side, the agent will always go to the side and consume ever more food at the expense of water due to the larger overall margin. We may attempt to balance things back and increase the importance of water, in which case we may end up in a situation in which the right state is now more valuable and the agent will move over again. A precise middle ground can be obtained, but which only forces the agent to decide in the middle state and stay on the left or the right side indeterminately, both of which states will have the exact same individual value. While these deterministic policies cannot describe a satisfactory solution, probabilistic policies can give some relief. Probabilistic policies also allow stochastic decisions, choosing an action with a certain probability and another action the next time a state is visited. In the multi-objective context, probabilistic policies are known to result in convex combinations of the utility of the involved deterministic policies. Due to the highly compressed nature of this problem, this structure is difficult to see in the traditional value chart. However, representing the exact same data and utility values on just skewed axes reveals more of the internal structure. Optimal probabilistic policies lie on the Pareto front, on this side of the convex polygon, representing mixtures of the previously discussed 2 deterministic policies. These policies are all of the exact shape of this distribution, in which the agent starts on the left side and then with some to be parameterized probability tunnels into the middle state from which it moves onto the right-hand side, stays there, and achieves the balance of objectives by first consuming only food and moving on and intermittently consuming only water, which of course is still very unsatisfactory because food then is lost intermittently. Interestingly, probabilistic policies allow a long-term balance, at least in weak probabilistic sense, of the objectives by defining a random walk over the state space that goes back between states arbitrarily often and visits all states infinitely many times. However, due to the frequent passage through the corridor state, these balanced policies do not turn out to be linearly optimal under any weighting and are discarded by the reinforcement learning algorithm. The nature of the proposed problem invites certain kinds of non-stationary policies, such as cyclic paths, in which the agent stays in the left state for a while, moves over to the right state, consumes water there, and moves back, and from there on cycles through the environment, which can be done one 5-cycle pattern or longer stay times, for example, staying 2 steps on the left and then staying 10 steps on the right. Linear reinforcement learning would not discover such a policy due to its non-stationary characteristic. However, we can evaluate its linear value, and it does again turn out to be not linearly optimal under any weighting due to the frequent passage of the middle state. Hence, linear preference can be shown to discourage balanced achievement of needs, because it only aims for an overall margin to be maximized. This can be seen in the geometry of the utility function. In fact, linear preference expresses needs that are entirely exchangeable, corresponding to food being able to replace arbitrary amounts and deficits of water. It's not always suitable to an environment. Past achievement can be shown to be irrelevant for future choices, regardless of previous lack of achievement or deficits accumulated. The future action will always go for the highest overall margin regardless of the past. This leads to an endless accumulation of imbalance over time and reinforces existing deficits. The proposed solution, multi-objective reward exponentials, or more, is based on the idea of existing negative exponential reward models. These model rapidly diminishing returns for high achievement as the value approaches -0. Low achievement, however, corresponds to an exponentially growing deficit. In the context of human single objective decision making, this is commonly used as a model for risk aversion. In the context of multi-objective optimization, however, it takes on a new meaning. If several of these terms are combined, one for each objective, and added, the overall value function can only be maximized if all objectives attain high values. This function has a natural interpretation as a soft minimum or soft AND function that only achieves high values if every component of its axis is maximized. Unlike the linear utility, this model does not correspond to exchangeable needs, but requires all components to be active and positive. Past achievement therefore determines future choices by selecting the option that achieves the overall highest balance of utilities by considering both past and expected future achievement. This idea can be formalized, and it can be shown that more can be solved by adding only a thin nonlinear layer on top of ordinary linear reinforcement learning. The key to this insight is to see that the more value function can be split into a weighting term that accumulates past attainment of individual objectives and can be interpreted as an exponentially changing dynamic weight of different objectives. If the original state space of the model S is augmented by also tracking changes of these objectives, existing reinforcement learning methods such as Q-learning or other value optimization methods can be used to estimate the best value of all existing alternatives. Only on top, the best action has to be chosen by picking the action that maximizes the more objective rather than the linear, while the inside term and the value estimation is still based on linear reinforcement. A detailed derivation as well as a detailed algorithmic description can be found in the article. Experiments first confirm the poor performance of the standard linear reinforcement. Standard Q-learning was applied by maximizing the sum of the individual needs and objectives. A discount factor of 0.9 was applied corresponding to a future time window of interest involving 10 time steps. As predicted by the initial analysis, the Q-learning develops a solution that intermittently accumulates food and completely neglects the need for water. An analysis of the state space traversal shows that this is realized by staying ever longer in the leftmost state 0, which corresponds to the previously discussed policy of going to the left and staying there, accumulating food, losing water. A further experimental baseline is obtained by deploying a greedy optimization strategy corresponding to a winner-takes-all strategy. Past achievement of objectives is tracked, and only just that objective or need is optimized that has been attained least in the past. This simple and greedy strategy is known to be highly susceptible to local optima. However, in our case, discovers a well-balanced solution corresponding to a 1-5 cycle, staying on the left to one step, moving over, staying 5 cycles there, and moving over to the left again. While this establishes a first balance of objectives, more outperforms the solution. Because it tracks future expected weight changes and thereby future expected needs, it can effectively plan ahead further and discovers a more effective 2-10 cycle strategy that stays on the left food side for 2 iterations, moves over, stays on the water for 10 cycles until the account's balanced, and then repeats the pattern. This strategy requires further foresight and achieves a higher overall reward and value under the more utility function. Linear preference has been shown to optimize solely for the highest overall margin, which discourages balanced achievement of different objectives in the case of conflict. The simple winner-takes-all strategy has been shown to achieve a course balance. However, the greedy nature of a strategy does not permit to discover longer-term interesting strategies. More, however, has been found to discover a highly satisfactory, non-trivial cycle, and in fact can discover longer cycles even, such as a 6-30 repetition pattern, if larger discount or time horizon values are specified. In conclusion, more is a new nonlinear preference function that allows to balance multiple objectives. It has been shown that it corresponds to a dynamic weight-changing pattern that dynamically gives preference to different objectives based on past attainment. This leads to a practical algorithm that only needs to add a thin nonlinear layer on top of ordinary Q-learning. In contrast to previous approaches, this is achieved strictly by mathematical derivation starting from a globally consistent preference function. Future work clearly needs to investigate the effectiveness of the proposed method for larger need systems. However, interesting contributions may also be achieved by looking for further theoretical unification and developing theoretic underpinning of existing approaches, as well as using more as a model for biological decision processes.